EDU-ARCTIC 2, Polar Research for Education, innovative program in Poland and Norway. Webinars.
So today I will explain about Northern Lights. It forms wonderful spectacles in the polar sky. I had this opportunity to see it live in reality. That's really amazing, and it's beautiful and really engaging. But today we will speak a little bit about the phenomenon per se. So from the physical perspective, not only from the beauty of this phenomenon. So why the Institute of Geophysics is interested in Northern Lights? First of all, it's beautiful phenomenon. It's geophysical phenomenon. It is the most important. But also we have the Polish Polar Station Hornsund on Svalbard. So you see on the map, Svalbard is far north. It's still not the North Pole, but it's more or less 1,000 kilometers from the Arctic Circle and 1,000 kilometers from the pole, so lying in between. And at this station, we do not only have the pleasure of observing aurora, and our team working there quite often record some videos or take photos, but we also measure magnetic properties of the Earth, so we can also predict where the aurora may be observed and if we are expecting the geomagnetic storm. So let's start with a video taken at the Polish Polar Station by one of the members of the wintering team, just to let you, just to give you some flavor of auroras. Sorry. Now we will change the perspective a little bit and we will look at auroras from the space. It's also a great spectacle. So now NASA's video with a time lapse of the Northern Lights seen from the space. It's really spectacular as well. Please observe the colors and the kind of movement that could be observed. So the colors here are visible. They are the most popular colors of aurora. So the Northern Lights are also called Aurora Borealis, and they are visible in the North Hemisphere, close to magnetic North Pole, or rather precisely saying close to Arctic Circle. On the south, auroras are also visible. They are called Aurora Australis or the Southern Lights. They are not that popular because they were not observed for centuries or thousands of years as in the Arctic. In the Arctic, we have people living constantly. We have indigenous people there. Around 4 million people are living in the Arctic, whereas in the Antarctic we mainly have only scientists or tourists. So and they are of course not present for centuries there. So that's the reason we quite often think about auroras in terms of northern hemisphere, but they are observed on southern hemisphere as well. They are visible in Aurora Oval, so the latitudes among 60, 70 degrees. And if the sun activity, we will speak about it later, is strong, then we may even have more than 200 nights with auroras per year. And auroras also occur on other planets of the solar system. For instance, they were observed at gas giants, so Jupiter, Saturn, Uranus, and Neptune. But Mars and Venus have also similar lights, which are formed differently. So the origin is different than the Earth's aurora, but some light spectacles are also observed there. Okay, and now very nice lesson by Michael Molina, who explains, and with great animation, explains the phenomenon in physical terms. So how it all starts and how the phenomenon is created. I hope you hear well and you see well.
Every second, 1 million tons of matter is blasted from the sun at a velocity of 1 million miles per hour, and it's on a collision course with Earth. But don't worry, this isn't the opening of a new Michael Bay movie. This is the journey of the polar lights.
The northern and southern lights, also known as the Aurora Borealis and Aurora Australis respectively, occur when high-energy particles from the sun collide with neutral atoms in our atmosphere. The energy emitted from this crash produces a spectacle of light that mankind has marveled at for centuries. But the particle's journey isn't just as simple as leaving the sun and arriving at Earth. Like any cross-country road trip, there's a big detour and nobody asks for directions. Let's track this intergalactic voyage by focusing on 3 main points of their journey: leaving the sun, making a pit stop in the Earth's magnetic fields, and arriving at the atmosphere above our heads. The protons and electrons creating the northern lights depart from the sun's corona. The corona is the outermost layer of the sun's atmosphere and is one of the hottest regions. Its intense heat causes the sun's hydrogen and helium atoms to vibrate and shake off protons and electrons, as if they were stripping off layers on a hot, sunny day. Impatient, and finally behind the wheel, these free protons and electrons move too fast to be contained by the sun's gravity and group together as plasma, an electrically charged gas. They travel away from the sun as a constant gale of plasma, known as the solar wind. However, the Earth prevents the solar wind from traveling straight into the planet by setting up a detour, the magnetosphere. The magnetosphere is formed by the Earth's magnetic currents and shields our planet from the solar winds by sending out the particles around the Earth. Their opportunity to continue the journey down to the atmosphere comes when the magnetosphere is overwhelmed by a new wave of travelers. This event is coronal mass ejection, and it occurs when the sun shoots out a massive ball of plasma into the solar wind. When one of these coronal mass ejections collides with Earth, it overpowers the magnetosphere and creates a magnetic storm. The heavy storm stresses the magnetosphere until it suddenly snaps back, like an overstretched elastic band, flinging some of the detoured particles towards Earth. The retracting band of the magnetic field guides them down to the Aurora Ovals, which are the locations of the northern and southern lights. After traveling 93 million miles across the galaxy, the sun's particles finally produce their dazzling light show with the help of some friends. 20 to 200 miles above the surface, the electrons and protons meet up with oxygen and nitrogen atoms, and they sure are happy to see each other. The sun's particles high-five the atoms, giving their energy to the Earth's neutral oxygen and nitrogen atoms. When the atoms in the atmosphere are contacted by the particles, they get excited and emit photons. Photons are small bursts of energy in the form of light. The colors that appear in the sky depend on the wavelength of the atom's photon. Excited oxygen atoms are responsible for the green and red colors, whereas excited nitrogen atoms produce blue and deep red hues. The collection of these interactions is what creates the northern and southern lights. The polar lights are best seen on clear nights in regions close to the magnetic north and south poles. Nighttime is ideal because the aurora is much dimmer than sunlight and cannot be seen in daytime. Remember to look up at the sky and read up on the sun's energy patterns, specifically sunspots and solar flares, as these will be good guides for predicting the auroras.
I hope you enjoyed the lesson by Michael Molina, and now I have 3 short questions, and please answer on chat. So what colors may aurora have? What are the most popular colors? Green, yes, definitely green is the most popular one. And green is obtained by excited oxygen. What else? Do you remember any other colors? Red, yes, that's great. This is also excited oxygen, but in the upper layers. Green, red, and purple. Okay. Blue, yeah. Okay, so we have all of them, the most popular ones. Recently, I saw some photos with white aurora. This is extremely rare one, but yeah, also may happen. So the next question is, sorry, because probably the chat is, yeah, now it should be better. So what words or phrases would you use to describe the movement of aurora in the sky? Because it's not constant. We see that it's not that the light, like artificial light that we lit up, but it's moving. So how could you describe this movement? Any ideas? Ribbon moving and fading, coming back. Great. Any other suggestions? I'm always thinking about a dance, like a dancing, beautiful queen with beautiful skirt or a dress that's moving constantly. Okay, and the last question, what atoms are getting excited and glow? So which atoms from our atmosphere are getting excited and give these beautiful colors? Oxygen and nitrogen. Great, thank you very much for your contributions. Okay, and the auroras could be described as an effect of a battle between the sun and the earth. So the sunstorms could have catastrophic impact on the Earth if we are not protected by the Earth's magnetic field. So our magnetosphere, which is the upper part of the atmosphere, in part of the ionosphere, in fact, protects us from the enormous energy emitted in the form of solar flares or coronal mass ejections, solar winds. But this energy gives us these fantastic spectacles in the sky. And how it starts. So basically the sun fires millions of tons of matter. And this matter travels with enormous velocity. It's approximately 2.5 million, but in case of very strong geomagnetic storms, this matter may even travel with the speed of 10 million kilometers per hour. So the quickest bursts of solar flares are traveling less than 1 day towards Earth. Also, the currents are imaginably strong, so they are much, much stronger. I will show you also on our next slides, comparing to other electrical circuits, how strong they are. And the solar flares are also giants. If we compare the solar flare and the size of the Earth, it's even this one, which was not the biggest one, but one of those that were captured, it's like 20 times more than the diameter of Earth. So we may imagine what kind of forces and energy the Earth is influencing when we have this magnetic, when we have this strong solar activity. Okay, I will, for the moment, I will close the chat. And what kind of solar activity we have? So, yeah, solar flares, coronal mass ejections, solar winds. There are different forms of solar activity. So the solar winds, the most common, let's say, is a stream of charged particles, which is released from the sun's corona, so the outer part of sun, and also the most hot. And it forms plasma with electrons and protons with enormous kinetic energy. So the particles escaping the sun's gravity, basically. If this escape is very sudden and we observe bursts of radiation, it's solar flare. Okay, and let's see a short video. This was captured by NASA, and this is 3 times. So the same, the repetition of 3 times, and they are time lapse. You see, in a moment, hopefully you will see. The hours are on the lower part, so it starts around 6, and then it lasts several hours till 2 p.m. So it's several hours. So it's not very sudden in terms of seconds. It lasts hours. But you see also the enormous size of that. The sun is covered by this red circle. Okay, and what is connected with sun? It's this solar activity cycle. So basically, the sun goes through periodic variations, and these cycles goes from minimum, in the solar minimum for several Earth years, we have very limited sunspots, or even we could have months with no sunspots at all. In 2008, we have a really deep minimum in solar activity, and for a few months we had no sunspots observed, not at all. And then it goes to solar maximum. And again, it could last some years when sunspots are very numerous. And then we could observe like several sunspots every day, every hour. And of course, the more active is sun, the more auroras we may observe. So auroras are highly dependent on the sun activity. And here is some solar cycles, and I wonder if you know how long the solar activity cycle lasts. So please also write on the chat. Yes, exactly 11 years. So now I may show here the years because I hidden that. And you may imagine that at the moment you see from that we are in the cycle number 25. And from where do we have this number 25? So the sunspot cycles were discovered in first half of 19th century. It was 1844, and later it was studied by scientists, and they were trying to, knowing that there are some cycles, they were trying to look for archival records of solar observations, And the first complete cycle, which was reconstructed, lasted from 1755 to 1766. So it was the historical cycle number 1, and we started numbering the cycles from that first reconstructed cycle. And at the moment, we are in the cycle number 25. As you see on this graphic, scientists are observing the weakening trend since cycle number 21. And they were even wondering if maybe this solar activity will be that low that the cycles will not have a significant maximum. And the first observation of the sunspots, which are from the 25 cycle, so they also indicated the start of 25th cycle, was observed by Polish astronomer Tomasz Mrozek in 2018 from the Space Research Center in Warsaw. And he observed some sunspots that are at the moment indicators of beginning of cycle 25. Unfortunately, at the moment, we are in the minimum, solar minimum part. So for the few coming years, the auroras will not be that intensive and often in our sky. However, in a few next years, then we should expect the solar maximum, and then hopefully the auroras will be more common. I promised to tell you how strong are the aurora's currents. So here you see 20 million amperes and 50,000 volts. If we compare it to the electrical circuit that we have at home or at school or in the office, our circuit breakers, so something that make us safe at home, will disengage when currents exceeds 50 to 30 amperes. So comparing to these 20 millions, it's really a small number. Okay, and now I would like to tell you about very spectacular events which took place in 1859. It is called the Carrington Event. In fact, it's named after British astronomer Richard Carrington, who noticed 2 dots of intensity bright lights appearing in the big group of spots on the sun. And it started a solar storm that was so strong that was observed not only in polar regions, but all over the world. And for a few days, people could read newspapers at night without artificial light. So it was unimaginably strong. So yeah, basically it's good to have this phenomenon, but from time to time, and from scientific analysis, we know that such strong event may occur every 500 years. It's really harmful for us, and especially now when we are using a lot of satellite communication, internet connection, etc. Such an event would be catastrophic for many days, and we would be without electricity, without satellite connections, without possibility to use GPS and many other navigation systems. And yeah, that would be a catastrophe. But let's watch this short animation about the Carrington Event. Okay, and one more short animation dedicated to what people thought about northern lights in ancient times. So before scientists could give explanation of this phenomenon, because you must imagine that if they didn't understand the phenomenon, didn't know about what's happening, it was definitely spectacular, but also for many of them probably frightening. So let's see about beliefs in ancient times. Okay, so for thousands of years, people marveled but didn't understand the phenomenon. And it was quite long, in fact, because only in early 20th century, a Norwegian scientist, Christian Birkeland, tried to explain the phenomenon, and he used, he was simulating the magnetic field with a device that he constructed by himself called a terrella. He explained scientifically the phenomenon, and basically it's what we understand from the phenomenon till today. So he was simulating magnetic field and putting so in a magnetized terrella, he observed that thanks to this magnetic field introduced inside, some light occurred around the poles of terrella, so quite the same as we observe in the Earth. He was also the first scientist to start geomagnetic field observation. So the first geomagnetic observatories were founded in Norway, and thanks to his suggestion, and he was the first to map the electric and magnetic fields in the North Polar region. Okay, and so coming back we started at the sun, and we know that there is this way of the charged particles towards the Earth, and we know that the Earth's magnetosphere is protecting us. However, from time to time, when the wind, the solar wind is really strong, the particles may enter to our atmosphere, and at the upper layers of the atmosphere, so mainly at altitudes 100, 200 kilometers, but even up to 1,000 kilometers above the ground, this spectacle takes place. So if the solar wind or the solar flares are strong enough, they are causing this so-called geomagnetic storm that disrupt the magnetosphere, and the particles may enter. And here we have information about the colors. You named them great after the first video, but we here have more summarized information. So basically the colors depend on which atoms are getting excited and at which height above the ground. So the oxygen gives us, there are the most common auroras thanks to excited oxygen. So green or yellow-green, and it's around 100, 300 kilometers above the ground. When it's higher, but it's quite rare, we have this red colored aurora. And for the nitrogen, we have violet and blue. or purple or blue, depending also how high from the ground we are. Why we don't have these colors or excited nitrogen at higher altitudes? Mainly because there is more nitrogen closer to the Earth, and the higher we go, the more oxygen is in the atmosphere. So that's why we have excited oxygen upper than 120 kilometers. Okay, and also we have so-called Aurora Oval. So the Earth has its own magnetic field, which protects us. But as mentioned at the video and also previously, we know that some particles may enter. In fact, they are forming a kind of tail on the night part of the Earth, and then the particles are coming back again, and in the weak parts, so in the magnetic poles, they may enter our atmosphere. So that's the reason that the aurora is visible mainly near the poles. It's not about geographical poles, but magnetic poles, which are slightly shifted from the geographical ones. And of course, they are formed in both hemispheres. So we may say around Arctic and Antarctic circles. Okay, and not only scientists are interested in auroras, but also many photographers and tourists are chasing auroras. There are some forecasts of the probability of visible aurora. How can we forecast auroras? Basically, we use for that magnetic observations, and we are measuring the magnetic effects of solar storms, and we use KP index for that. So this is the magnitude of geomagnetic storms, and this KP index value from 0 to 9, where 0 means small disturbances, and 9 huge disturbances. If we have index of 5 or higher, then it indicates a strong magnetic storm, and auroras are very possible. We do not have time today to go through the activity of chasing aurora, but I encourage you to use this activity from the GRASP platform, where students may first check where auroras are possible. If there are no auroras at the moment, they may look for some historical data from last 30 days, or even a quarter or longer. So NASA is making available databases with geomagnetic observations, and they may find KP indexes high enough to have auroras. They may also compare K indexes in lower and upper altitudes and compare them to KP, so planetary index. So I encourage you to go through that. All the links are included in the GRASP package, so it's easy to follow and to look for this data. Okay, and you already know that the Earth is not unique in terms of aurora, because auroras are also observed mainly on gas giants, so Jupiter, Saturn, Uranus, and Neptune. Why? Because they have strong magnetic fields, and also they produce their own atmosphere. So basically, they have conditions for auroras to create there. Of course, why we know that? Using measurements from spacecraft, for example, Cassini, images from telescopes like Hubble Space Telescope, the scientists have been able to verify that our neighbors, planet neighbors, have their own auroras. They were also trying to find auroras on other planets because we know about auroras on gas giants quite long, but what about other planets? It's not that obvious. So Mercury has a magnetosphere, so we could expect aurora there, but there are no auroras. Do you know why? Any ideas, please send on chat. So what is necessary to create? Yeah, perfect. Yeah, in fact, it's not a question of being close to the sun, so that the particles cannot be trapped. But the problem is lack of atmosphere. So Mercury is too small and too close to the sun to retain an atmosphere. So basically, if there is no atmosphere, so there are no molecules that could get excited by the solar winds. So it means no aurora. Great. So what do we have next? Venus. Here the story is different because Venus has an atmosphere. But in case of Venus, the problem is that it doesn't have a strong magnetic field. But scientists could observe something similar. It's not exactly aurora as it's formed on the Earth, but some light phenomena are observed on Venus as well, because the magnetic field, in fact, is produced by the charged particles from the sun. So for the time being, when the solar wind passes Venus, some magnetotails are produced, even though that normally Venus doesn't have this strong magnetic field per se. But from time to time, such spectacles are observed. But this is a different light phenomenon than our Earth aurora. And the last planet to be described, it's Mars. And for quite long, in fact, it's the latest discovery about auroras on other planets. It comes from 2016, when scientists discovered that Mars, in fact, could have or have auroras. They are not formed by the poles, so this is also different from what we observe on the Earth, and it's different because it's also diffuse aurora. So it's not like particles entering the magnetic poles, and also not particles interacting with a magnetic field, but it's like energetic particles rain into Martian atmosphere. But some phenomenon could be also observed, and if an astronaut stands on the surface of Mars, he might see an aurora, faint and blue, and also not like on Earth, not necessarily near the planet's poles. Okay, and now the wrap up. So I will give you a chance to summarize a little bit, so with 5 remarkable facts, and we will have a short quiz afterwards.
Have you seen this amazing video of the Northern Lights? The footage was filmed in Sweden over Christmas 2013, which got us thinking about the Aurora Borealis. Here are 5 remarkable facts you should know. I'm Sophie, and welcome to the countdown. What causes an aurora? Well, the Earth is surrounded by a magnetic field, which normally helps deflect harmful radiation. When charged particles from the sun, known as the solar wind, fly towards our planet, the field speeds up those particles and directs them towards the magnetic north and south poles. As the solar wind hits our atmosphere, the charged particles collide with atmospheric atoms and molecules and transfer their energy. These gas molecules then spit that energy back out in the form of light. Our atmosphere is mostly made up of oxygen and nitrogen, which produce a variety of colors. Atoms of nitrogen release blue light, while two nitrogen atoms bonded together give off a purple hue. The color also depends on altitude. Oxygen releases green light above 100 kilometers, but switches to a reddish color above 240 kilometers. And when colors combine, they can produce other shades, like pink and yellow. The aurora can be a single hue or a shimmering rainbow. Unfortunately, the solar activity that gives us auroras also has some unwanted effects. On the planet's surface, charged solar particles can interfere with satellite communication, along with radio, television, and telephone signals. Navigation instruments, like compasses, become unreliable. The solar weather can even cause electrical surges that interrupt the power grid and sometimes result in power outages. Auroras have fascinated humans for thousands of years. This cave painting, which dates back to 30,000 BC, may represent the earliest observation of the phenomenon. But it wasn't recorded in more detail until 2600 BC, when a Chinese manuscript described it as strong lightning. Most early attempts to explain the aurora fell flat. A drawing from 1570 AD attempted to illustrate it as a line of candles hovering above the clouds. In 1619, Galileo thought reflected sunlight was causing the light show, so he named it after the Roman goddess of the morning. It wasn't until the 20th century that Norwegian scientist Christian Birkeland suggested molecules in the atmosphere were responsible for the light show. The Aurora Borealis and its southern cousin, Aurora Australis, are generally located over ring-shaped regions roughly 4,000 kilometers wide, which circle the north and south poles. But when an aurora is putting on a big show, the ring spreads over a much larger area. On rare occasions, Aurora Borealis can be seen as far south as Texas. If you want to see an aurora yourself, you can either travel north or south, or just wait for a particularly large aurora. You'll want a clear, dark night, and you should avoid heavily populated areas with a lot of light pollution. Then, just look up and marvel.
Okay, and 4 questions, or 3 or 4 questions as a wrap-up. So please indicate where auroras may appear. So near the North Magnetic Pole, is it true or not? Near the South Magnetic Pole, on Mercury, or on Jupiter? Please answer on chat. Any ideas? Please indicate all the places where aurora may appear. So yes, thank you very much. So near the North Magnetic Pole, near the South Magnetic Pole, and on Jupiter, whereas on Mercury, we do not have atmosphere, so we do not have this opportunity to auroras to form. Okay. So the aurora occurs when highly charged electrons from the solar wind interact with elements in the Earth's atmosphere. True or false? Oh, we have true and false, and true again. So basically true. And the most popular color of aurora is green. It's connected with excited atoms of nitrogen, oxygen, or argon. Yeah, nitrogen and oxygen. That's true. And the argon doesn't glow, doesn't get excited and glow. Yeah, and the green aurora is connected with oxygen. So nitrogen produces other colors. Okay, and the last one, auroras are mainly formed at altitudes. So this mainly is important because it can be up to 1,000 kilometers, but it's mainly forming at which altitude? So 1 to 2, yeah, 100 to 200 kilometers. Okay, great. Thank you very much. And I encourage you to look for the website that have live cameras. For instance, from Lapland, there is a camera that goes every day and records the night sky. And if you are lucky, you may watch this aurora from your sofa, but seeing how it's visible in the northern Finland. As we know, at the moment we have the minimum solar activity, so the auroras are not that often visible. So if you would like to make sure that you will see an aurora, I have a last proposal for you to create your own aurora in a fluorescent lamp. So let's see how we can produce this artificial aurora.
We see northern lights on the screen behind me. It is a light phenomenon observed in the upper atmosphere near our planet's magnetic poles. Is the formation of the northern lights a simple process? Rather not, but I will try to explain it in a simple way. The auroras are the result of disturbances in the magnetosphere caused by the solar wind. The solar wind is a stream of charged particles, protons and electrons, emitted by the sun. Near Earth, the flight paths of these particles are deflected by the Earth's magnetic field. The change in the trajectory of charged particles occurs in the solar wind and in the magnetospheric plasma. The resulting ionization and excitation of particles in the atmosphere emit light of different color and intensity. The aurora-like phenomenon can be induced at home. I will replace the solar wind with a walkie-talkie, and the atmosphere, with an energy-saving fluorescent lamp. As you can see, the fluorescent lamp is not connected to electricity. When I bring a walkie-talkie and a fluorescent lamp closer, the aurora effect occurs. The white aurora is very rare. Therefore, I will use another fluorescent lamp. This one is glowing green. This effect is more like the natural Aurora Borealis. It is also important that holding the fluorescent lamp by the screw does not cause electric shock.
Okay, so thank you very much for your attention.
Watch other recordings from webinars on our YouTube channel, youtube.com/EDU-ARCTIC. EDU-ARCTIC 2. From polar research to scientific passion, innovative nature education in Poland and Norway receives a grant of 240,000 euros received from Iceland, Liechtenstein and Norway under EEA funds.